In this video, we continue with chapter 7.2 about diagonalization of matrices. And we are going to continue with the problem we left off on in the last video, where we showed by hand that the diagonal matrix corresponding with P inverse AP is this matrix right here with 3, -2, and 2 on the diagonal. Those are our eigenvalues. So we're going to see now how to do this diagonalization in Sympy. So in Sympy, the diagonalization is in an equivalent form, but it still works. So in linear algebra, the square matrix A is diagonalizable, or sometimes called non-defective, if it's similar to a diagonal matrix. And so that's saying there exists an invertible matrix P and a diagonal matrix D, such that either one of these relationships is true. These are equivalent. So you could say P inverse A, P equals D, or you could say A equals P, D, P inverse. So when we do diagonalization in Sympy, it returns a tuple P and D where D is diagonal, but it does it in the opposite order where we get M equals P, D, P inverse. So just know that you're going to get the opposite order in Sympy. So the P's are going to be different, but if you verify P, D, P inverse, you still get the same results. All right, so we've got our matrix A from the previous example right here, and I typed it in. And then the command in Sympy is to say P comma D equals A dot diagonalize function. Leave your parentheses empty in the function. And then it'll save P and D as matrices for you. So if you type P enter, you get out matrix P here. And if you type D enter, you get out the matrix D here. Now note that the matrix D here that Sympy gives us has the same eigenvalues, but in a different order. That's okay, because if we verify P times D times P inverse here in Sympy, we still get out our original matrix A. So when you do diagonalization, if you want to do it in Sympy, that's fine. Just be aware the matrix P that you get and the diagonal D that you get are not going to be the same that you're necessarily going to get if you do it by hand, because Sympy uses the matrix equals P, D, P inverse. And if you do it by hand, following the techniques in our book, you do it that the D equals P inverse AP. So you get slightly different values, but it's still okay. And it's still going to work out as possible diagonalizations here. So let's talk about diagonalization and linear transformations. So far in this section, the diagonalization problem has been in terms of matrices. So we can think about diagonalization in terms of linear transformations. So we state that as for linear transformation T mapping V to V, does there exist a basis B for V such that the matrix T relative to B is diagonal? And the answer is yes, when the standard matrix for T is diagonalizable. So let's take a look at an example. So we want to find a basis B for the domain of T such that the matrix for T relative to B is diagonal. So T is this linear transformation right here. It maps R3 to R3. So the first step for us to solve is to find the standard matrix for T. So we get that down here just by taking the coefficients of T and plugging them into matrix A, and I've defined it over here in Sympy as well. Just typing in my coefficients. So the first row is -2, 2, -3. The second row is 2, 1, -6 from the coefficients on the X, Y, and Z here. And the third row is -1, -2, and a 0 because there's no Z in the third tuple of this linear transformation. And so then to find the eigenvalues, I did it in Sympy right here. So -3:2 tells us -3 has multiplicity 2. It's a repeated eigenvalue, and eigenvalue 5 comes up once. And then you can find the eigenvectors in Sympy also. And so you can see those correspond with, if we do it by hand, same results. And then we take those eigenvectors and use those to construct our basis. So it doesn't matter what order you put the eigenvalues in to construct the basis. So there's our basis, and then the matrix of T relative to the basis is this A prime, where that's the matrix here with our eigenvalues, our diagonal matrix. So here is how we got P and D in Sympy. So you just say P comma D equals A dot diagonalize is your command. And then you get out P and D. Notice D has the eigenvalues in a different order. It's okay, and matrix P is going to be a little different because you can still verify that if you do P multiplied by D multiplied by P inverse, you get back out our original matrix A here. And then you can even use what's known as a Boolean, the double equals here, to see, does P multiplied by D multiplied by P inverse equal A? And this Boolean double equal, or what's known as the equality operator, will tell you true or false. So a Boolean expression is an expression that evaluates to just a true or false. Those are known as Boolean values. And so if we say double equals here, instead of telling us if something is a value or not, it tells us true or false. And so we got our true here, so we verified it. So this is a cute thing you can do when you're typing up your lab assignments if you want to verify with Sympy. Okay, next we will cover section 7.3, which goes more in depth into diagonalization, and we will continue to use Sympy in our calculations.